Hi, I am Jorge Mendez, and in this video, I will give an overview of our recent survey on lifelong learning and compositionality. As a disclaimer, I will not be covering many specific papers or citations, so if you're looking for those, please check out our paper, which has tons of references from fields like lifelong supervised learning, lifelong reinforcement learning, modular neural nets, neurosymbolic learning, hierarchical reinforcement learning, and many more. Instead, in this video, I'm going to describe general trends, assumptions, and trade-offs of popular classes of approaches to both lifelong learning and compositional learning in reinforced and supervised settings. As one additional disclaimer, even though it is 2023, I will not be talking about large pre-trained models. I do have thoughts on how they may or may not be applicable to lifelong compositional learning, so feel free to reach out if you want to chat about that. Lifelong learning gets rid of the standard IID assumption of machine learning models. Typical learning methods assume access to a bunch of data drawn from one distribution and are evaluated on data from that same distribution. But in the real world, data is non-stationary. The data distribution changes over time. One simple example of this notion is a robot faced with tasks one after the next. Recognize plates, recognize kitchen appliances, recognize cleaning supplies. This formulation of non-stationarity as task sequences is very common in lifelong learning. And in this video, I'm not going to go into a discussion of whether that's a good formalism or not. So I'm just going to take it at face value. In this setting, it is reasonable to ask the lifelong learner to do well on new tasks, which is typically referred to as forward transfer, do well on previous tasks, which is described as avoiding catastrophic forgetting or achieving positive backward transfer, and scale to many tasks, which requires limiting the memory and compute growth as the number of tasks increases. And one concept that encompasses these three requirements is that the agent should discover knowledge that is reusable, applicable to future and past tasks without the need to add repeated or redundant information to the agent's knowledge. The key takeaway of this video and our paper is that compositionality is a tool that is especially conducive to reusability. Compositional knowledge can be combined in various ways to achieve forward transfer. The addition of new knowledge requires only modifying a small subset of components, avoiding forgetting or of knowledge that requires no update. And compositional knowledge can solve combinatorially many problems, which inhibits growth. Let's make things a bit more concrete and talk about how we formalize both lifelong learning and compositional learning. Guido van de Ven and Andreas Toljas give us a nice categorization of lifelong learning problem formulations. In the task incremental setting, the agent sees tasks one after the next and is told by an oracle which task it is currently facing, task 0, 1, 2. In this setting, the joint distribution of inputs and outputs varies from task to task, and the agent can distinguish the functions mapping inputs to outputs thanks to the task indicator. The cost function that these agents optimize at time t is the sum over tasks indexed by t prime of the per task loss function using the model for task t prime at time t. So the model updated with any knowledge obtained between time t prime and time t. In the domain incremental setting, the agent does not get to see which task it is currently facing. Instead, only the input distribution varies across tasks, but the conditional distribution of outputs given inputs is constant. And still the agent optimizes the sum over task costs. In the class incremental setting, the agent faces a multi-class problem incrementally, with classes being presented for training one after the next. An equivalent way to see this problem is that the agent faces multiple tasks, and its goal is to simultaneously predict the task and the class label. This equivalent formulation allows us to use once again the same multitask objective. Now, these definitions say nothing about how one task relates to another, and here is where compositionality comes into play. We focus on a form of functional composition, where we view tasks as transformations of inputs to outputs that can be decomposed into sequences of transformations. This view, formalized in terms of a compositional problem graph, allows us to describe single task learning, where transformations are individual to each task, standard multitask learning, where all transformations are shared across all tasks, and compositional multitask learning, where intermediate transformations are partially shared across sparse subsets of the tasks. As one example, consider a visual system solving the following 4 tasks. Count the number of cats, locate the largest cat, locate the largest dog, and count the number of dogs. A compositional agent could learn to detect cats and dogs, count, and locate largest from the first 3 tasks, and then solve the 4th task by combining the dog detector with the counter. In our paper, we categorize approaches along 6 dimensions. Is the method single task, multitask, or lifelong? Does the method implicitly or explicitly receive cues in the input that give away how one task relates to another? Does the method tackle supervised, unsupervised, or reinforcement learning problems? Is there any form of composition, and if so, is it temporal or functional? Are the components aggregated in a flat manner, chained in some fixed order, or arbitrarily combined into a graph? And what application domain does the method tackle? Check the paper for an in-depth description of this categorization. Most work on lifelong learning has focused on supervised or unsupervised setting, and most efforts have gone towards avoiding catastrophic forgetting in image classification. I'll describe 4 common classes of approaches. In the paper, we separate those into task-aware and task-agnostic, but I will skip that in the video. The first family of approaches regularizes models to stay close to the solutions to previous tasks. This solution approximates the true multitask objective for the previous tasks with a data-driven regularizer. One common example is elastic weight consolidation, which places a quadratic penalty on the model parameters for moving away from their original values. Another technique encourages the solutions to different tasks to lie on orthogonal subspaces of the parameter space. A more recent form of regularization is functional regularization, which penalizes the model's predictions instead of its weights by encouraging the outputs of the model to stay close to their original values. The next family of methods is replay-based mechanisms. Here, to compute the approximate objective for previous tasks, methods rely on a replay buffer that typically stores data from those previous tasks. The vanilla technique simply subsamples data from all past tasks and includes a portion of this data in each gradient computation when training a new task, which approximates the multitask training setting. Some works have developed cost functions for the previous task, while others have defined mechanisms to construct the replay buffer, including with samples that are different from those seen during training. In most cases, replay-based methods outperform regularization-based methods, since they enable simultaneously retaining knowledge that is useful for previous tasks while adapting to new tasks by not restricting update directions. One special case of replay methods is generative replay, which replaces explicit replay buffers with a generative model that hallucinates replay samples from those earlier tasks. While in principle generative methods are created to reduce memory requirements, unfortunately the generative models are themselves quite large, so this gain isn't entirely obvious. More importantly, generative replay is typically a lot more computationally expensive, and computation today is a lot more expensive than memory. Another potential pitfall of generative replay methods is that the generative model itself also has to be trained in a lifelong setting, and usually this is achieved via self-generated replay. Broadly speaking, expansion-based approaches add capacity to neural net models over time as needed to account for new tasks. On the surface, this seems closer to the idea of knowledge reuse that we're looking for, since models could reuse any part of the knowledge and build upon that with extra capacity to adapt to the new task. However, in practice, works in this space have used capacity expansion mainly as a means to avoid catastrophic forgetting. While most methods from the past 6 or 7 years have focused on avoiding forgetting with the techniques we talked about, some approaches have aimed to discover knowledge that can be reused for future tasks, in the spirit of this video. Ella is one early idea that discovered a set of basis linear functions that could combine to solve many tasks. Another approach selects whether each layer in a neural net should be shared or task specific, but misses the idea that layers created for new tasks should be available for future tasks to enable full reusability and compositionality. One other technique explicitly meta-trains features to be reusable across tasks. There are certainly techniques that fall outside of this categorization, so be sure to check out our paper to see these different lines of work. Compositional learning has evolved as a mostly disjoint line of work. The first kind of methods that learn compositional knowledge receive a hand-engineered modular configuration as input and learn a set of modules from data. A prime example is the neural module networks of Jacob Andreas and collaborators, where the structural configuration is parsed from a question in natural language, and the modules are represented by small neural nets that perform various types of visual transformations. Let's briefly look at the kinds of problems that these neural modules can solve and how. Recall our earlier example of visual processing of cat and dog images. We can learn to count cats, detect the largest cat, count dogs, and detect the largest dog, with a neural module for cat detection, another for dog detection, another for finding the largest, and another for counting. Stacking these modules appropriately into bigger networks would give us a complete set of solutions. Back to our forms of compositional learning methods. Other approaches assume that the modules themselves are given, say as programmed functions or previously trained neural nets, and the agent searches for the combination of those functions that solves each problem. There are also approaches that receive neither the structure nor the modules. In visual question answering, many methods observe a number of question structure pairs and use those to learn a mapping from questions to structural configurations, in addition to learning the modules. In our paper, we describe all these methods as receiving explicit information of the structure of the tasks. Some other techniques in this space assume that the inputs contain implicit cues of what the structure of the task is. For example, an image of only cats would require only cat detection. In other cases, this information is not provided at all to the agent. Say, if there are both cats and dogs in an image, and the agent has to find the largest cat. In these situations, the agent must search for the appropriate configuration for each task individually, sharing the modules across tasks. All the methods I just described operate in the multitask setting, where the agent receives data from many tasks at once. In the lifelong setting, the agent receives data from one task at a time and must extract configurations and components from the continual stream. Most approaches to this continual setting assume that each component can be learned on a single task and then kept frozen for all future tasks. While this works in some restricted settings, it isn't hard to imagine that many modules trained on a single task won't be readily applicable to other tasks. So more recent works have developed more complete methods that initialize modules intelligently, choose how to combine them for each new task, determine when new modules are needed, and update existing modules over time. While this line of work has received little attention, it has produced very promising results, including zero-shot compositional generalization. Lots of recent works have taken the stance that compositionality should arise in non-compositional architectures. We discuss the applicability of this to the lifelong setting in our paper. Most work to date on lifelong learning has focused on supervised settings. Of the works that do apply to RL, many have mimicked supervised approaches to learn a single network and avoid forgetting earlier tasks, with regularization or replay approaches. Interestingly, replay in the RL case requires a number of special considerations that don't affect the supervised case, such as dealing with non-stationarity in the data from each task, or handling the distribution shift that occurs after updating a previous task's policy. Apart from this, researchers developing lifelong RL methods have placed more emphasis on reusability than their supervised learning counterparts. Successors of Ella have used factorized transfer to reuse knowledge across policies, while others have learned separate per-task models for each task and reused other elements for accelerating future exploration. Compositionality has been at the heart of RL for decades, and as such, there have been many different definitions of what constitutes a component in reinforcement learning. In this video, I will focus on differentiating temporal and functional composition, but in our paper we describe various other forms of composition and compare them to the functional case. Temporal composition has been the most common form of composition in RL, with the main example being the options framework. Roughly, an option module arises a small policy and packages it for reuse in many situations. Our paper focuses on functional composition, where instead modules correspond to functional transformations of the input. To view the differences between these, consider this example from robotic manipulation. An EWA arm trains to pick up a can of Coke, lift it, and place it to the right. Temporal decomposition could extract modules such as grasp, lift, place. If we then wanted to solve a task like insert can into shelf, we could compose these along with new rotate and insert modules, using one of these modules at a time. This task could also be decomposed in functional space into grasp pose detection, pick and place trajectory planning, and EWA motor control. This decomposition would allow us to solve the same task with another robot manipulator, say a JACO arm, by learning a JACO motor controller and composing all these elements simultaneously into a JACO pick and place policy. Very few works have tackled lifelong compositional RL for any notion of compositionality. This ability to learn and improve knowledge over time and reuse it in various combinations to solve decision-making tasks has been one of the main motivators of the lifelong learning field. Yet, research in this space has barely advanced in the last decade. One line of work that has sought to promote progress is the creation of benchmarks for studying multitask, meta, or lifelong RL. Some promising evaluation domains to study these properties include MiniGrid, MetaWorld, RLBench, Causal World, and CompoSuite. Our perspective is that compositionality is a tremendously promising tool for making progress towards solving the lifelong learning problem. It is a natural and general mechanism for reusing knowledge. It enables targeting future updates to a sparse set of modules, which helps avoid forgetting. It has shown some highly encouraging results in the few settings where it has been studied. And progress toward non-lifelong compositional learning has developed tools that are readily applicable to lifelong approaches. We close our paper by sketching out 7 promising directions to follow toward developing impactful compositional lifelong learning research. Please check those out. Thanks for watching.